This week, we're talking all about the multivariate normal distribution. So you should all at least be familiar with this guy. This is something that we've been working with for a long time, and is something that you've seen in stats classes before, I hope. This is the normal density function. And this is the univariate normal density function. So this is what a normal distribution for one variable would look like. This is its multivariate cousin. And so this may look intimidating at a glance, but it's really quite similar to what we've seen and what we've learned using what we've learned about in terms of matrix notation. We could sort of break it down and figure out exactly what's going on with it. So the most important difference is that there are obviously more than one variable when we're dealing with multivariate data. But the biggest difference is that we have this sigma matrix. So what does this have that the normal sigma squared doesn't? So essentially what we have is our covariances. So in a standard normal distribution, we just have, or in a normal distribution, we have variances. We don't have any covariances between multiple variables. So let's compare the multivariate to the univariate normal distribution piece by piece. And obviously we're starting pretty similar, which is essentially just that we're going to be dividing by something. So in both cases, we're starting out by saying we're going to divide by something. And so let's look at the denominators here. So the denominators in this division are for the univariate normal distribution is square root 2 pi sigma squared. And for the multivariate version, it's 2 pi raised to the p divided by 2 times the determinant raised to 1 over 2. Now remember, raising something to 1 over 2 is the same thing as taking the square root. So this determinant of the covariance matrix to the 1 over 2, that's saying we're taking the square root of the determinant of the covariance matrix. And p over 2 is raising the square root of a number to the p power. So that first part is essentially saying we're taking the square root of 2 pi and raising it to p. So now we're sort of seeing where we get these similarities. We're taking this square root 2 pi raised to p. So that's kind of like this piece here, except now we're raising it to p. And then we're replacing sigma squared with the square root of sigma squared with the square root of the determinant of the covariance matrix. So they look different, but they're essentially the same idea. So the sort of cooler part and the more important part is the exponential part, which is actually the numerator, because remember we're multiplying 1 over the denominator we just saw by e raised to 1 over 2 in both cases, which is just a constant, negative 1 over 2, to these things. Now, so we can look back at the univariate normal distribution. We see this is up here. And so let's think about how these two things might be similar. This probably looks somewhat familiar. And so what this essentially is it's the sums of squared error, or deviations from the mean, divided by the variance. So note that one way we can rewrite this univariate piece is by sort of factoring it out, or just changing the order, changing the notation. And we can write it as x minus mu times sigma squared raised to the -1, because this is raising something to the -1 is an inverse. So this would be the same thing as writing 1 over sigma squared, and then times x minus mu again. So here we have x minus mu squared, essentially, just here and here. And then we are multiplying it by 1 over sigma squared. And so that gives us the same thing, just a way of rewriting this here. And now it starts to look a little bit more similar to the multivariate component over here, where we have what are, instead of single variables, we have a mean vector or we have a vector, a mean vector. Remember, mu bold is a mean vector, and x bold is a vector. And then the inverse covariance matrix, and then again the vector minus the mean vector. So again, this is a way of saying squared error, because you have the deviations from the mean vector twice, and then you're dividing by the covariance matrix because you're taking the inverse of the covariance matrix. Very similar, it's exact same idea. So what about this on the right that we have here? Does this look like something else that we've seen before? Maybe something that we learned about last week? Maybe something like this. What was this called again? Does anyone remember? Take a second to think about it. But this is something that we talked a lot about last week. And so this is the quadratic form. So essentially what we're doing is we're centering our x by the mean and the inverse covariance matrix. And then so it's the quadratic form of the centered x and the inverse covariance matrix. So this is similar to dividing the sums of squared errors by the covariance matrix, as I mentioned. So based on what we learned about last week as well, if the eigenvalues of sigma, the covariance matrix, are denoted by lambda, what are the eigenvalues of the inverse covariance matrix? And so think back to what we learned about the spectral decomposition and how we can use it to get the inverse of symmetric matrices. And so in this case, it turns out that the eigenvalues are just going to be the inverse of the eigenvalues, 1 over the eigenvalues, or 1 over the lambdas. So if we wanted to obtain the constant distance, the way we've learned about for the quadratic form, except we're using the inverse covariance matrix, what would that look like? And so remember, the way we get this is we take how we get the ellipses is we divide c by the eigenvalue, but the square root of the eigenvalue. But in this case, we're taking the inverse of the square root of the eigenvalue because we're taking the inverse of the covariance matrix. So for the reason that we just saw here, we have 1 over the eigenvalue. So here we're taking the square root of 1 over the eigenvalue, and the square root of 1 is 1, multiplying by the eigenvector. So in this case, it actually turns out the ellipses are defined by c times square root eigenvalue times eigenvector. And so we can visualize the bivariate normal density, or the bivariate normal distribution, the same way we visualized quadratic forms using eigenvectors last week. So I'm going to use an example where I'm simulating 3 observations, and they're drawn from normal distribution with mean vector 3 and 6, and covariance matrix over here, variances of 2 and 3, and a covariance of 1. So this is just going to be an example. I'm just going to show you what 3 data points along the multivariate normal distribution look like, and hopefully this will make some of what we learned about last week a little bit more intuitive as well. So I'm starting by simulating my data. So there isn't a random number generator, I don't believe, for the multivariate normal built into R, but of course there are packages that have it. So I create my matrix, create my mean vector, my covariance matrix, create my mean vector, and simulate my data. So here are my simulated points. So each of these points is a point that's drawn from the multivariate normal distribution with this covariance and this mean vector. So if I want to plot my observations, I start by obtaining their centered form. So I take x minus mu. So I take the first row of my data minus the means. So this is the centered version of the data. So this data now has a mean of 0 instead of the actual means. So this is the second observation and third observation. So now these are deviations from the mean. And I get my eigenvalues of my covariance matrix and my eigenvectors of my covariance matrix. And so I can start by getting the constant distance of the first observation. So this is my centered. This is the centered version of the first observation that I got before. So so this is x minus mu times the inverse of the covariance matrix times x minus mu. And that gives me my constant distance for the first observation, which turns out is 0.57-ish. So now I can find the point I need to plot along the two eigenvectors with c times square root of eigenvalue times the eigenvector. And so these are my two points that I want to plot. And so that's how I can get the constant distance for this variable. So this is a lot like what we did last week, where we got these vectors that have the specific distance that are related to the constant distance and the eigenvalues. And note here, the way I structured these axes, the left and bottom axis are centered at 0, 0. So this would be the centered version of the data, but the top and right are centered at the mean. So this is the mean vector, so 3 and 6. So this would be our mean vector if you look at it, the uncentered data, which are the top and right versions of the axis. So now I can add my ellipse around these vectors. And so now let's go and see where our original point lies on this plot. So this is the uncentered version of our original point, and this is the centered version. So this is just the first randomly drawn observation, and this was the observation minus the mean vector. And note that this point is right here. It's right along the ellipse, but it's not actually on one of the eigenvectors or eigenvalues. These just define this sort of density ellipse, which is a representation of constant distance for the multivariate normal distribution. So let's add a second observation. So this point was originally at 1.13 and 9.17, centered down here. So now here's this ellipse. For this point, I didn't show every step in the procedure, but this is the same, again, similar to what we did last week. We're seeing a different constant distance based on a different data point. And if I add the point, again, note it's in a different direction. It's on the other side of this second eigenvector, but it's also along this ellipse. And finally, observation 3, we can plot in green, is over here, also along the green ellipse. So what we're illustrating here is that these ellipses are a way of defining the multivariate density. Any points along the same contour or ellipse can be considered equidistant from the mean vector given the covariance matrix. This is referred to sometimes as Mahalanobis distance. I may not have pronounced that correctly, but that's one of the terms you'll see for it sometimes. And so the distance of any point for that can be drawn from, treated as part of a multivariate normal distribution, which again is parameterized by the mean vector and covariance matrix, is defined by the quadratic form. And so we get these c squares, and that tells us the distance, which is defined by these ellipses, which again are defined by the eigenvectors. And we can see that any point on this red ellipse would be considered to have the same distance from the center as any other point along the red ellipse. It also turns out that c squared, the constant distance in its quadratic form, are distributed chi-square with p degrees of freedom, where p is the number of variables, which is a convenient result. So we can see that the c squared values from our simulated contours were 0.57, 8.49, 1.67. So I can actually use the p chi-square function to get the probability associated with the chi-square value of each of these. So here I'm getting chi-square so I'm getting the probability for chi-square of 0.57 with 2 degrees of freedom, and turns out that's 0.25. So that means that the blue line, the first line, contains 25% of the observations from the normal distribution. Would be considered the 0.25 density region. It's sort of like would be sort of like taking the center 25% from a normal distribution. That was univariate. This is the center 25% from the multivariate normal distribution. So the red and green lines had the following proportions, the following densities inside of them, 0.99 and 0.57. So the red line is 0.99. The chi-square value there was 8.49. So we can really think of this like the tail of the distribution. This is most of the density of the distribution is inside of this tail. And so we can look at it back here and we could sort of see what we're talking about here. So this red ellipse, inside this red ellipse is 99% of the density of our distribution, joint density of our distribution. And then inside of the green one is 0.57 and inside of the blue one is 0.25. And so we can simulate our bivariate normal density in Plotly as well. And I intended to do this before I started the video, but I forgot. So I'm going to copy all this code. And I'm going to open up blank R, get rid of all this. And then I'm going to run these. So this is the same thing that we saw. What I'm doing is I'm simulating 10,000 observations from a multivariate normal distribution. That way I can simulate the full density surface, and I'm going to open it up in Plotly. We'll give it a second to load up. I think I shared this. I didn't share the R console when I did this, but I ran that code. And so this is the joint multivariate density. And so we can see it from different angles here. And so we can take a look and see where some of our points were. So if we say take observation 3, so this was 3.888 and 8.23, and we find that in Plotly. So x1 is 3. Circle this around so it looks okay. So x1 is 3.88, so it's somewhere around here. All right, 3.99, close enough. And what was 3.88 and 8.2? So 3.88, 3.99, and then so it's hard to do this kind of, but we can sort of see it here, something like that. So we see the ellipse here. It's a little bit hard to see on this Plotly graph. So that's the top-down version. You can look at it. It would be somewhere sort of around here. So we could see the height there. And so we could see what proportion of the density is inside of that that ellipse defined that point lies on. So the last thing that I wanted to look at was what happens when we look at different matrices with different covariances and what that implies for their shapes. So here we have a covariance matrix with 0 covariance. So this implies that the two variables that we have are completely independent. And actually, let's look at it where they're not completely independent, where they're actually 0.1. I meant to change the other slide, but I forgot to do that. I just changed the second one. So here we have the variances are 2, the covariances are 0.1, so very small covariance, not quite 0. just makes it a little bit easier to see how the shape changes with this. So here I plot the ellipses with the 25, 50, and 75th quantiles. So 25% of the density is inside the blue, 50% inside the red, and 75% inside the green. And so we see here when the covariance is very low, we get very circular shaped ellipses because the densities are not there's not much covariance between the two variables, so they're essentially independent. And so with this matrix, when we have high covariances, let's see what this does. And so we see here we got very narrow ellipses where it goes very significantly in one direction, and then the eigenvector is very short in another direction. And so this illustrates what covariances do to the shape of the multivariate distribution. So when two variables covary a lot, when they're highly correlated, the multivariate distribution becomes more oval shaped. And if they were perfectly correlated, it would just become a line, and we can treat it as a univariate distribution. And when two variables don't covary much, the multivariate distribution becomes more circular. And so, while we can't easily visualize it, these principles extend beyond more than two variables, of course. It's just we can only really visualize the bivariate density. And we could also see this when looking at the eigenvalues. So here we look at the eigenvalues of the matrix that had very low covariance and then very high covariance. And what we see is that when covariances are high, at least one eigenvalue is going to be much larger than the other ones. And when they're low, the eigenvalues are going to come closer and closer together, and they would be equal and just be represented by the variances if the variables were completely uncorrelated. And so this is going to be an important principle throughout the course, where we see how the size of the eigenvalues is determined by the covariance matrix, and covariance matrices with a lot of covariance will tend to have one or a few very large eigenvalues. Why this is important will become clear later in the semester.